Hi, this is Dan Buller, retired electronics engineer, sitting on the front deck of my houseboat again. These all start the same way. I want to talk to you about an interesting problem I ran into at Next Test. And it's kind of fun, and it kind of came up in my mind because I posted something on Stack Overflow. You know, I'm trying to go back to Law 5, which is that the harmonics always have a phase offset of 0, 90, 180, or 270 relative to a sine wave. For a cosine wave, that's Davor's law, and it's 0 and 180. But these people are stupid. So I posted this really cool image that I have. It's really great. When you have a distortion, and Wikipedia used to say this, and I don't know where it went, but they've changed their stuff on harmonics and everything. But harmonics are not caused by transients. Harmonics are not caused by noise. Harmonics are caused by defects in the electronics, like going over the peak of some sine wave, or, you know, hitting a zero crossing distortion in a class B amplifier, those kinds of things. Distortions in the transfer function. And that's what I'm doing. I'm simulating those things in Excel. Now, why do I go that way? Why do I just assume that noise is not involved? Because noise is not repeatable, not at all. I mean, if you're driving down the road and you hit a rock, are you going to hit another rock at exactly the same place, exactly at the same time? Or are you going to hit 50,000 rocks in a row at exactly the same place on the tire? No way, absolutely not. But if you run over a nail and that nail sticks in the tire, and as you drive down the road you can hear it, you'll hear it and you'll know it. And if you go faster, it'll speed up, and if you go slower, it'll slow down. That's the kind of thing that harmonics are. Running over a gravel road, that's not the same as running over a nail in the road and hearing it hit the pavement again and again and again. So noise and harmonics are two different things. That's why there's a specification called THD plus noise. THD plus noise includes all the harmonics and all the noise. Now, if you do just THD, it goes just the harmonics. It goes and sums up just the harmonics. THD plus noise is pretty much everything. So let me tell you this story. I was working at Next Test, and we had a guy. I was the only mixed signal guy on the group because this was a new product, and Mike Furland and a bunch of other guys were in on it. Dave Reynolds was in on it. A bunch of guys were on it, but I was the only apps engineer that was really working on it. And the reason they hired me is that my boss Rick went to Mike Furland and said, "Who's the best apps engineer you know?" And he said, "Dan Bullard." Because I used to stop by Mike Furland's office all the time. He was a brilliant guy, and he had all the data sheets, all the data books on all kinds of parts. And so I'd go there and look through his data books, and we would chat, and talk about things, and we got to be pretty good friends. And he's like, "Okay, you're the guy, you're gonna be the guy." So he's the guy who got me hired at Nexa. So but we did have another guy named Grant Veman, who was he was doing microcontrollers, and I've done microprocessors. I worked on the not just the Intel stuff, but on the Motorola stuff too. The MC6809, the MC6800, and all of those. And microcontrollers are very similar. Most microcontrollers have at least one DAC and at least one ADC on them. And so you can digitize analog waveforms with a microcontroller and store it in a memory, or you can generate a waveform like a sine wave. You can use a microcontroller to generate a sine wave and send it out of the DAC. Whatever whatever kind of thing you want to do, you can do all kinds of stuff with it. microcontrollers are very cool, very cool. And so Grant did a lot of microcontrollers, and so he picked a Philips microcontroller for us to test with the next test, Lightning. And that's what it was shooting for, was microcontrollers with DACs and ADCs and stuff like that, you know. Grant didn't know anything about mixed signal, but he did know something about microcontrollers and DACs and ADs, a little bit about DACs and ADs. So Grant picked out this microcontroller, Philips microcontroller, and we started working on it together, and we developed a test program for it, and we came across something that just freaked us out, because we didn't know if the hardware was ready. Maybe the hardware wasn't working. You know, we were using Applicos hardware, and we had problems with Applicos before, and they actually had to send one guy out to work on a problem that we had. So we were testing this thinking we didn't know what the problem was, but we're getting a big DNL failure. That's differential nonlinearity. A big DNL failure in the DAC. We couldn't figure out why. So we poked around, and I decided, hey, let's do an equivalent time sampling test. So I did equivalent time sampling on the place where it was failing, right around the 3F to 4-0 transition. So 3F, that is hexadecimal, 3F to 4-0. That's 0, 1, 1, 1, 1, 1, 1, and 1, 0, 0, 0, 0. So we're getting a big glitch right there. And so I took a look at it with equivalent time sampling, and we figured out what I was doing. It was amazing, the resolution. If you look at it, you can see the clock coming through. That's the clock that we gave it from the next test. And then you get this big glitch in the transition from 3F to 4-0. Again, that's hexadecimal. And so that's 0, 1, 1, 1, 1, 1, 1, and 1, 0, 0, 0. So when all those ones change over to zeros and the MSB changes to a 1, you get this big negative looking glitch. Well, the easy workaround for that is that you move the sample point away from the transition, the digital transition. And so we did that, and it worked just fine. And so then we had something, we realized, oh, it's not the tester, it's not the Applicos hardware, it's their part. So Rick says, hey, you need to talk to Philips and get him to come in here and look at this thing and tell us about it, Now, they were, I don't know what they were using this microcontroller for. Some people said it was to light LEDs on a shoe, I don't know. But this guy came over, Kamalpati, that was his name, Kamalpati. Okay, so Kamalpati was there, and I was going through how we did this on his controller, his Philips product, and he was in Philips. And I showed him this glitch, and he's like, ooh, that doesn't look good. I says, yeah, that's, what's happening there is pretty obvious. What's happening there is that the MSB is slower than the other bits. And so the other bits go from 1, 1, 1, 1, they go, it's 0, 1, 1, 1, 1, and all those lower bits that are ones flip to 0. Before the MSB goes to a 1. That's just a defect in the way they did it internally in the chip. So he looked at that and went, whoa, that's not good. That's definitely not good. I said, well, have you guys seen this before? He says, no. This is the guy who's in charge of testing this Philips microcontroller, among other things, lots of other Philips products. So he was stunned, and he says, are you showing this to anybody else? And I said, well, yeah, that's like, the fact that we can do this cool plot is like great troubleshooting tool for us, and we can show customers or potential customers what we can do for them. And he says, okay, I don't mind if you show it to people, just don't tell them it's from Philips. Well, that's understandable, I guess. He doesn't want to be embarrassed. So he understood it. The really hilarious thing was that a year later, we had gotten some success testing or selling the Next Test Lightning. A year later, somehow we ended up getting Kamalpati to come back for a demo. And I did pretty much the same demo for him. And you know what happened? He looked at that and he says, God, I can't believe we never saw that. We never, ever saw that. That's why you're not using the right machine to test your parts. You know, our tester found it. How come you're not finding it? I never did buy our tester. And I'd done a lot of work for Philips. I worked for Philips in Taiwan, in England. I did a class in Southampton, England. It was really, really kind of fun. I worked for Philips in San Jose. I worked for Philips all over the place. And Kamalpati, he was a nice guy, but he's like, please don't tell people about this. I said, okay, I won't, I promise. But it's a wonderful picture. I mean, it shows exactly what's going on. And what I did with it was, I used it to measure glitch energy, because that is a spec. There is a spec for that. They didn't do it, but to measure glitch energy, basically cut it off at the 3F point. You just cut off the glitch, and then you integrate the area in there, and you can measure the glitch energy in nanovolt seconds. Now, this glitch, if you run this part, you run a sine wave through this part, notice this 3F to 4.0. This is going to happen somewhere in the middle, well, somewhere in the sine wave. Depends on where the sine wave is based. But this glitch can cause you problems. What will it cause you? It'll cause you harmonics. It'll cause you harmonics, because it's like the nail in the tire driving down the road. So you'll hear it. You'll hear that thing. You'll see that glitch being hit again and again and again, and that'll cause harmonics. And that doesn't go away, and it doesn't move from 3F to 4.0 to like 6.2 to 3.7. It doesn't change. It doesn't move around. It always stays there. It's a defect in the product. And so harmonics don't move because they're caused by malfunctions in the device. Malfunctions in the transfer function, not random crap. It just happens randomly like noise. Noise is random. And even if the noise isn't random, let's say the noise is from 60 hertz, chances are very, very good that your device is not running anywhere near 60 hertz or is not based on 60 hertz. And so even if it's not random, it may happen at a random time relative to your signal. So when the signal hits you, you don't know what the phase of the 60 hertz is relative to your device. So it's kind of a fun thing. Kamalpati, he was a nice enough guy. He put up with me doing 2 demos for him a year apart, and he still couldn't believe that they had never seen that. Now, like I said, I don't know if this device was used for, lighting LEDs on a shoe, or whether it was used to run a drone. I don't know. But, you shouldn't allow hardware to do this kind of thing. Devices should not be doing this. And this is a race condition. This is just bad design. And I've had, Chromatic, I did the PSRR test on their device, and I found that they had a terrible, 0 dB PSRR, that is power supply ripple rejection. So if I put a sine wave in on the power pin along with the DC power for the DAC, it caused the signal to come straight through. So they had to go back and redesign the hardware. For a device, RAM bus or anything else, you would think they know what they're doing, but nope. So they had to redesign the hardware. And this thing, same thing. They should redesign the hardware. But, for them it wasn't worth it. For Philips, they didn't care. They're just lighting LEDs on a shoe. Who knows, hopefully they're not flying drones, and hopefully they're not doing important things. But you know, I badmouth Philips. They had some pretty good stuff. They did a good job. They wouldn't give the source code for their test programs to the guys in Taiwan because they knew that if they did that, the guys in Taiwan would modify the test program and would make the yield higher. And so they get more money for making the yield better. So they got paid more money for making the yield better. So if they could find a way to cheat and get the yield up, they'd do that. And they would do it, no questions. I mean, these guys are really something. Now, I love people in Taiwan. They're nice folks, but they'll rip off their grandmother. They'll steal from their grandmother if it means they can get some more money. So most people are like that. I'm not like that. I don't cheat. I don't lie. I don't steal. I just don't do it. I mean, if I get caught doing that, my reputation is toast. I mean, I can't even go back to Taiwan anymore because of TrueTest. Because I went in there saying we could do it, we couldn't do it. Next Test couldn't do it because they had a failure in their software. It wasn't my fault, but I thought we could do it, we couldn't. So, be true to your word, try to be true, try to do the right thing, don't rip people off, try to always do the right thing. You'll have a better reputation if you do that. If you're a scumbag, people will know you're a scumbag. Okay? Anyway, I thought that was a fun story. So once again from the river, this is Dan Bullard. See ya.